Okay, this is going to be a supplementary lecture over some of the problem sets here in chapter 2. I kind of wanted to go over some of these. Obviously, they won't be the same as what I have entered in digitally, but they will be along the same line. So I want you to be able to work these kinds of problems, and the best way to do that is to go over them. So let's take a look here. We're going to start with number 1. The half-life of phosphorus 32 is 14.3 days. What interval of time is required for 100 millicuries to decay to 25 millicuries? What time is required for decay of 7/8 of those atoms? Okay, so to go through this particular process here, we're going to start with our equation here regarding activity. So we've got the activity at some time is going to be equal to the initial times e raised to the lambda t. Now in this particular case, we know that lambda is going to be equal to 0.693 divided by the half-life. We know what the half-life is. That's 14.3. So that ends up being 0.04, I believe that's 0.46. Let's work that out on the calculator just to make sure, because I want you guys to make sure I'm not making a mistake here. Okay. So we've got 0.693 divided by 14.3. Okay, so that's 0.04846. Okay, so there we go. Now, we're looking for the interval of time for it to go from 100 millicuries to 25 millicuries. So we type all of that information in here. We now know what lambda is, so we need to solve for t. So how do we go about doing that? Well, we divide both sides by the coefficient here of the e. That gets rid of it over here and puts it as a denominator over here. And that leaves us with e to the minus 0.04846 times t. If we take the natural log of both sides, and let me go ahead and draw that out here. If we take the natural log of this as well as this, what happens? Well, what happens is we end up with natural log of 25 over 100. This, I don't like the way that's written. That should be, and I'm going to use the stylus here. As soon as I plug it in, plugging it in is generally a smart thing to do. Let's see. There we go. Okay. There we go. Got recognition. All right. So we'll go here. The way I would like to see this written is natural log of 25 divided by 100. I don't want you getting confused like it's the natural log of 25 divided by 100. No, it's the natural log of that fraction. So I want to make sure that you know that. Now over here, we have the natural log of e to the minus 0.04846 t. Now, the natural log of e is eventually going to be 1. But before we do that, we have to take this stuff right here and we have to move it out. Now, let me write up here this equivalency. You may remember from logarithms, and you may not. Even if you don't, this is still true. You may remember that you can take the exponent here of whatever you're taking the natural log of and make it a coefficient. So that's what we're doing here. This stuff right here becomes a coefficient. Now the natural log of e ends up being 1. So that's where this equation ends up coming from. You've got the natural log of 25 divided by 100 is going to end up equaling minus 0.04846 T. Okay. Solving this for T, we end up finding the value here of the natural log of 1/4. If you actually work this out on the calculator, which let me stop this for just a second. If you clear all of this out, bring this up here like this, if you take 0.25, which is the same as 1 divided by 4, or if you take 25 and divide it by 100, that's what you come up with. You take the natural log, that's what you've got, 1.38629. So that's where this comes from. So this disappears, this becomes this, and is still equal to this garbage over here on the side. So you got a negative number here, you got a negative number here. If you divide both sides by this negative number here, then over here, and again, let's go over here, put a negative here. And what happens when you have a negative divided by negative? They become positive. So then you take 1.38629, you divide it by 0.0486, and you end up with this, 28.6 days. So that's the interval of time it is required to go from this to about 1/4 of that. In order to be able to find the time required for decay of 7/8 of those atoms, rather than use 25, you could just take 7/8 of 100 here, and you would end up with 12.5 millicuries. So you could take the 12.5, replace the 25 with that, and then work the problem the same way, and you come up with the answer. Okay, so it's really, that's probably really not too difficult. There's just a number of steps there that you got to remember as you go through. Here is the solution for that second part, following the same equation. Put in 12.5 as opposed to 25, crank through the same type of algebra, and you come up with 42.8 days. Okay, so not so bad, not so bad. All right, let's move on here to number 2. So a radioactive needle contains radon-222, where the half-life is 3.83 days. And that is in secular equilibrium with radon-226, which has a half-life of 1600 years. So how long is it required for the radon to decay to half its original activity? Well, if you're looking for the radon to decay to half its original activity, there you go. That's a fairly easy one. But we have problem 3 here. And a lot of this information here is going to be solving this particular problem. So the one thing I want you to remember here regarding secular equilibrium, secular equilibrium has graphs that look like this, with the parent nuclei up here and the daughter nuclei coming up and approximating it. Remember, this is when the half-life of this, in this case uranium, is significantly longer than what you have here for the half-life of the daughter product. So again, here in nature, we've got radon-226, which has a half-life of 1600 years. It exists in secular equilibrium with uranium-238. What fraction of the world supply of radium will be left after 1600 years? Okay, So we know that the half-life of radium here is 1600 years. They tell us that. We can determine here what lambda is if we know what the half-life is. And we have that particular information. Now, we're looking for the fraction that is left after 1600 years. So what's left after 1600 years, we're going to use this particular equation. The amount that we have here, the number of atoms, is equal to the original amount that we had, e to the minus lambda t. So the amount or the time here for uranium to decay is going to end up being, pardon me. So we take 6.693. We know this is the half-life here, so we can determine what lambda is. That looked like a T there for a minute. I'm sorry, I couldn't figure that one out. Since we know what lambda is, we can put it in here. We know the amount of time because it's asking us how much is left after 1600 years. What they have done here is they have taken this particular equation and they have divided both sides by n naught. And when they do that, you get the fraction of what's left. All you have to do is to crank through this particular expression. So you take 1.5 times 10 to the minus 10 years to the minus 1 times 1600 years, put a negative on it, exponentiate with that exponent, and it turns out the fraction here, which they need to denote, not, is equal to 0.999, or if you change that to a decimal, 99.9%. In other words, almost all of it. All right, number 4. If a phosphorus-32 radionuclide decays for an interval of time equal to its average life, what percentage of the original activity remains? Okay, so we have the average life, which is going to end up being a 1.44 times the half-life. And that turns out to be this. We also know that T here is in that same amount of time. We know we come up, or not T, but lambda, sorry. The way they have these things written, that's throwing me off. We have 0.0485. So we can use our activity equation here. We know that the original activity, we're just going to say it has 100. I mean, it can be anything, but generally we're just going to start here with 100 to make the computations easier. We know what lambda is. We know what amount of time the average life happens to be, so we're plugging that in. And this over here, I should note as well. Is going to be days to the minus 1, since that's lambda. Once you crank through all of this, you find out that A is going to be 0.3683 or 36.83%. Another way to work this is the same way as what they did up here. If you take both sides of the equation and divide it by the original amount that you have here, if they had done the same thing here, you would have ended up with that same expression, or that same answer, I should say. In other words, rather than substituting that in with 100 there, you could have just said A divided by A naught. after dividing both sides by that. That way, whatever you end up with here is a fraction, much like what you saw up there. So finally, the fifth problem here. What are the wavelength and frequency of a 1 MeV photon? So if the energy is 1 MeV, that's a way of expressing that in EV, mega electron volt. We know that the energy is h nu, and we're going to try to have to figure out exactly what this nu actually means. So we solve for it. We know what h is. We know what this constant is. Since we know what this is and we know what the energy is, all we're trying to do here is compute this into joules for later on. The number, or nu, ends up having to be 10 to the 6th electron volts divided by 4.13 times 10 to the minus 15th EV seconds. And when you do that, you end up here with the frequency. In other words, this is the number of cycles that go through a particular point per second. Now, how do we determine what the wavelength is? How do we determine all of that? The way that you do that, or the relationship that you need to remember in order to be able to do that, is when it comes to photons, the wavelength, which, let me see if I can figure out how to do this. No, let's try this again. Sorry, drawings are really bad. Let's see. There we go. So the wavelength times the frequency should equal the speed of light. This was key in order for us to be able to figure out what the frequency is. We've got that. Now that we have the frequency, we know what the speed of light is. We basically divide both sides here by the frequency, and we end up with a wavelength. So that's the basics on how to solve these particular problems. I'll have something very similar for you on the homework.